Thanks so much for being here today. I'm going to share my slides. I actually titled this presentation Making the Case for Methane Mitigation instead of just the fastest way to slow warming, because I think there's a lot to methane that I wanted to cover here. So I'm assuming everyone can see my slides. Monica, maybe just give me a thumbs up. Okay. Awesome. So as Monica said, I am currently at Spark Climate Solutions. For those of you that aren't familiar with this organization, it is a climate nonprofit, fully philanthropically funded, and we focus on reducing emissions of super pollutants or non-CO2 climate forcers that are difficult to reduce, specifically from the sources that are difficult to reduce. So for example, methane from enteric emissions from livestock and nitrous oxide from fertilizer, things like that. So that's what we focus on, and I've been there for the past year. Before that, I was at the Special Presidential Envoy for Climate Office at the State Department, working on a bunch of things, but including accelerating methane mitigation efforts globally. Before that, Environmental Defense Fund, where I worked a lot on methane. And so I'm coming to you today as a scientist who has studied methane impacts on climate for around 15 years now, and not just how methane influences the climate, but also how our different mitigation actions can benefit the climate over different timescales. And I focus a lot on turning the science into action. So I do pursue original scientific research that I publish in the scientific literature, but everything that I do is geared towards actionable science and things that insights we can take and use to make the most effective decisions to reduce emissions of super pollutants and short-lived climate pollutants, and I'll get into the difference in a little bit, and specifically methane. So I've worked with companies and governments to provide scientific guidance, and I cannot overstate how important it is, the work that you all are doing. And as someone who's just the scientist, knowing how important the action is, but not actually taking the actions myself, I'm just so personally grateful to the methane mitigation community for all of your efforts. So thank you so much. And my goal today is really to just support this community by arming you with the scientific facts and resources that you need to market the value of methane mitigation in your businesses. And so let's start with just where we are today. Everyone here knows that addressing the climate crisis is an urgent imperative. Temperatures are quickly rising, which has devastated communities across the globe as the planet has reacted dramatically in response. We have more intense hurricanes and heat waves, and in some places we have more intense downpours, and in other places we have more intense droughts. So we're in a situation where we can't just think about the future and in terms of limiting warming over, long periods of time, but we need to think about right now, what can we do to create a safer climate for everyone? And so in order to address climate change, we need to mitigate the major drivers of today's warming. Nearly all of today's warming is coming from human emissions. And so this includes a mix of different types of emitted compounds. And so it includes gases that are known as greenhouse gases that trap heat in the Earth system. This includes carbon dioxide, which emissions of CO2 are responsible for around half of the warming that we're experiencing today. Methane is the second largest driver, contributing to around 30% of the warming that we're experiencing today. And then we also have nitrous oxide and halogenated compounds. That's what HCs stands for here, which are fluorinated compounds like CFCs that are still lingering in the atmosphere, warming the climate. Their predecessors, or they're what came after them, the HCFCs and then the HFCs and also SF6, and all those other compounds are bundled together as HCs. And then you all would be familiar with nitrous oxide, which is also contributing significantly to warming today. So these are the greenhouse gases that are driving today's warming. But then we also have something called indirect greenhouse gases. So these are species like carbon monoxide and non-methane volatile organic compounds, VOCs, and they themselves are not trapping heat, but they react in the atmosphere in ways that increase the amounts of other greenhouse gases, like methane, but also tropospheric ozone, for example, ground level ozone. That is not shown on this chart because we don't emit it, but we emit other things that then produce it, and it's a greenhouse gas and it causes warming. And then finally, we have a sunlight absorbing particle known as black carbon, which is also responsible for some of the warming that we're experiencing today. And so these emissions come from a variety of sources. You can see those on the bar chart on the right. And most of those sources are emitting multiple types of climate pollutants. And so the colors, you'll see on the next slide, the colors of the different emitted compound names will change, but the slices, the colors of the slices align with the sectors on the right. So today, of course, we are going to focus on methane. And specifically, I divided this presentation into 3 different sections. The first is 3 reasons why methane mitigation is the fastest way to slow warming, and then 5 factoids to use for inserting the importance of methane, and then 10 resources to consult for more information. And when I talk about that, I'll go into a little bit more detail about what you can find in the IPCC reports that have already been released, and then what you can expect in the forthcoming assessment report, which is the 7th assessment report that Monica mentioned. And so while methane has many diverse sources, as you can see on this bar chart, and as you all know, because you represent the different sectors and sources that methane comes from, each of these sources will require unique mitigation measures specific to that source. And those are insights that you all know a lot better than I do. But the fundamental motivation for mitigating methane applies to all sources. And so using scientifically robust and consistent messaging across the mitigation community can help strengthen our collective efforts, which is why it is important to have this kind of cross-cutting organization that Monica's put together so that we can all be consistent together as we try to make the case for methane mitigation, bring more attention to it, bring more resources to it, for example. So let's start by diving into arguably the most important motivation for methane mitigation and why we really are here today, which is that it is broadly considered the fastest way to slow warming. And it's often even referred to as a climate emergency brake. And so there are 3 key reasons why. So the first reason is that methane is the largest share of short-lived climate pollutants. And I'm going to unpack what this means. So if you look at the pie chart, you can see that we have a mix of long-lived compounds that we emit and short-lived compounds that we emit. And so the long-lived compounds, most notably CO2, are the ones that can last in the atmosphere for centuries. They build up over time. The warming that we're experiencing right now from CO2, for example, is from this buildup over time, the past 100 or so years of us emitting CO2 continuously into the atmosphere, which then sticks around for a long time. And so we have this warming that's from that combined effect. And that also applies to nitrous oxide and several of the halogenated compounds as well. Now, so that's in the blue color in this pie chart. Now, in the pink color on this pie chart are the short-lived climate pollutants, most notably methane that we're all familiar with, but also the indirect greenhouse gases and the aerosol, the absorbing aerosol that we emit into the atmosphere. And so these short-lived climate pollutants, they only affect the climate for the matter of days to a couple of decades. And so every time we emit them into the atmosphere, they stick around for a bit and then they're removed from the system in various ways. And so they're not committing us to long-term warming in the same way the long-lived climate pollutants are. This means that almost half of warming from short-lived climate pollutants today is almost entirely from recent emissions over the past decade. So what that means is when we start reducing the amount that we're putting into the atmosphere, it can have a really big impact on the climate. And so just a quick nod to super pollutants in this context. Super pollutants are climate pollutants that are far more potent per mass than CO2 at warming the climate. It's basically everything on this pie chart that isn't CO2. And when you do the math, we emit around 100 times more CO2 today than we do all these other pollutants combined. But because they're so potent, they end up causing around half of the warming that we're experiencing right now. So that's what a super pollutant is. And short-lived climate pollutants are a subset of super pollutants. So they are super pollutants. They are potent, but they're short-lived. And so what this means is, like I said, the short-lived climate pollutant impact is largely from recent emissions. So this impact could be eliminated quickly by reducing emissions, unlike long-lived climate pollutants. And there's a lot of different analogies out there to kind of describe the difference between the short-lived and the long-lived. Monica and I have discussed them in detail. Some are better than others. One that I really like as a visual is to think about these different pollutants as like a kitchen with two sinks. So you have this faucet, which is emissions from human systems, and you have the short-lived and the long-lived. And that short-lived drain is going pretty fast. So we're entering the short-lived into that sink, and it's going pretty fast. And the long-lived climate pollutants, that drain is really, really slow. And so for the short-lived climate pollutants, if we start decreasing the amount of short-lived climate pollutants that are coming out of that faucet into the sink, well, then it'll be removed quickly, and we will lower the amount of water in that sink pretty fast. So this concept is from Will Atkinson at RMI. He gets full credit for it, but I think it's a really compelling visual that just kind of helps you think about the difference between the short-lived and the long-lived. So another analogy that I've heard just quickly that I find really funny is that methane and short-lived climate pollutant mitigation is like Ozempic. So it's like really fast acting. That was one from the climate minister of the UK. So the second reason that methane mitigation is the fastest way to slow warming is that it is not co-emitted with major climate cooling pollutants. So something that you may have noticed that just popped up on the bar chart here is that we also emit climate pollutants into the atmosphere that cool the climate. And they also come from all the same sectors. But you can see that the methane sources, like agriculture, fossil fuel production and distribution, which is like natural gas leakage, for example, you can see, and waste, you can see that there's far less cooling coming from those sectors. On the other hand, the major sources of CO2, like power generation and industry, have a lot of climate cooling pollutants. And so these climate cooling pollutants are short-lived also. So the CO2, when you emit the climate cooling pollutants and the CO2 lasts for a really long time, causing warming, and the climate cooling pollutants don't last very long. But even so, that means in the near term, when we reduce emissions of CO2, if we're also going to reduce emissions of the climate cooling pollutants, then what happens is that we are unmasking some of the warming that we otherwise would be feeling if we weren't also emitting those climate cooling pollutants at the same time. And so this is another reason why methane, in contrast, can be more efficient at limiting warming in the near term, because it is a straight benefit to the climate when we reduce methane, and you don't have this unmasking effect. The third reason is that we have readily available solutions to immediately cut methane emissions in half. So the purpose of this presentation is not to go into detail about all the different mitigation measures we have available, which again, you all know better than I do anyway, but it's to show you that because we have these strategies available right now with existing technologies, this does not include any kind of dietary behavioral changes, we can immediately reduce our impact on the climate by mitigating methane if we are able to deploy these solutions quickly. And so on the bar chart and the pie chart here, you now see that there are some hashed sections that are showing how much methane we can reduce from the individual sectors and overall based on existing strategies that we have today. And again, this is in contrast to CO2, where reducing CO2 in many cases requires a global energy transition, which will take time to get to that point. And so this is another reason why methane mitigation can be faster and more beneficial for the climate in the near term. So when you put all of this together, the largest share of the short-lived climate pollutants, and it's not co-emitted with major climate pollutants, and we have readily available solutions to immediately cut emissions in half. You could see the temperature responses on the graph on this slide, which is showing just the temperature responses to future methane emissions from 2020 to the end of the century. So the black curve here is no action to reduce methane, and we see that we have around 0.9 degrees Celsius of warming by end of century. This would blow past our temperature targets. We cannot achieve our temperature targets without reducing methane. And if we were to cut methane emissions in half by mid-century, we would end up, just with existing technologies, we would end up avoiding around 0.5 degree Celsius of warming, which is really powerful. But the faster we act, the more warming we could reduce in the near term, which is around 0.25 degree Celsius. So these are really large numbers, and this is really exciting, and this is why we're pushing so hard to deploy all the great mitigation measures that we have available right now. So the methane warming still goes up over time because in this case, even though, for example, we're reducing methane emissions from cattle with our existing technologies, we're still growing the population and feeding more people and developing different nations and eating more cattle. So we have more cattle. So that's why the warming impact still goes up. But this graph is just showing you with existing technologies right now. It doesn't include emerging innovations. So the hope is with emerging innovations that are on the horizon that we're working on right now. My company, my organization is very engaged in that. For example, we can lower this further in the long run. All right, so switching gears now to 5 factoids to use for asserting the importance of methane. And so number one, I had to throw this in there because this is methane potency. This is what everyone uses. I actually prefer not to use this one, and I'll explain why. But essentially, methane is 80 times more effective at trapping heat than carbon dioxide over the following 20 years after equal emissions and mass. This is also known as the global warming potential with a 20-year time horizon. And it's also around 30 times more effective over the following 100 years. Both of these things are true. It matters the amount of time after the methane and CO2 are emitted that we are comparing their climate impacts. So this graph on the right-hand side shows you how methane's potency relative to CO2 changes over time. And so it starts out really high because methane is really potent. And then the methane starts being removed from the atmosphere, mostly through oxidation. The CO2 is also removed somewhat, but sticks around a lot longer. And so methane's impact declines over time. I'm not going to go too much into other metrics and the challenges here in the presentation, but there's a lot of this that has to do with physical science. And so I'm happy to answer any questions in the Q&A about why this metric, what about other metrics, what about GWP star, for example. All that kind of stuff is fair game for asking me because it's based on physical science and it can be really confusing in the stakeholder world. And I understand that. So again, happy to answer questions about that. But the reason why I don't prefer using this, stat is because sulfur hexafluoride, for example, SF6, we emit it into the atmosphere. It is around 20,000 times more potent than CO2. So that's far more potent than methane. but we don't emit enough of it to have a really large impact, which is not why it's on the pie chart. It's less than 1% of today's warming. So sometimes I feel like this can be a little misleading because it matters how much methane we're emitting and how much CO2 we're emitting. And that's where the CO2 equivalence then comes from. You multiply the GWP by how much methane we're emitting to get a sense of what this actually means in terms of climate impact relative to CO2. So I mentioned why methane's potency declines over time. I added this text in here because I hope this deck can serve as a resource for you that you can revisit. So I added a lot more language on this slide than I normally would, but just also wanted to flag why is methane more potent than CO2 in general. It has to do with two things. One is its molecular structure is more capable of absorbing more heat, but also because when methane is oxidized in the atmosphere, it leads to the formation of other greenhouse gases. This includes tropospheric ozone, which I mentioned earlier. It also includes stratospheric water vapor, and it also includes CO2. When methane is emitted from biogenic sources like livestock, for example, it's not adding any CO2 into the atmosphere because the carbon cycle is that CO2 is going into the grass, which is being eaten by the cow, which is being burped up in methane, which is then going back to CO2. But when we have fossil sources of methane, such as through natural gas, then that CO2 would otherwise have been carbon stored for a really long time. So that is additional to the atmosphere. So in any case, around 1/3 of methane's current warming impact is actually from these effects on other greenhouse gases. And so that contributes to why methane is so potent. All right, so the second key fact, this is the one that I prefer to use relative to the potency. And you don't have the issue of different time horizon. It's basically methane's impact on the climate right now from emissions. And this represents how much methane and its impact we could reduce with targeted measures to reduce methane. So methane emissions from human activities have caused around 0.5 degree Celsius of warming since pre-industrial times. This means that methane is responsible for around 30% of today's warming from climate warming pollutants. So I also have a note in here, again, for your reference later. Sometimes you'll hear that methane is responsible for half of today's warming, because right now the climate is warmed around 1 degree Celsius, a little bit more now in recent years, but 0.5 degree relative to that 1 degree is half of warming. But that 1 degree Celsius of warming that we see right now includes the cooling impact. So it's 1.8 C of warming that we would have from the climate warming pollutants, and then around -8 from the cooling pollutants. So I strongly recommend using 30% of today's warming is coming from methane, because if it's half, then what does that mean for CO2 that's responsible for around 0.8 C of today's warming? The math doesn't add up. And so these I think are more powerful stats to use than methane's potency. All right, for the third methane factoid is its near-term impact. And so this is a fun fact that a lot of people don't know, but it's basically that this year's methane emissions from human activities will cause around the same amount of warming over the next 10 years as this year's CO2 emissions from human activities. So this is shown, it doesn't matter, I don't have a y-axis here because it doesn't matter what that warming is. When we're just looking at a single year's worth of emissions, the degrees are really, really small and mostly meaningless. But basically what you're seeing here is we have as much warming coming over the next decade from this year's methane emissions as we do from CO2. But the CO2 lasts for a really long time, which is why we need to do everything in our power to reduce that impact. And methane doesn't. And so that you can just think of then that potential for reducing that impact in the near term if we start cutting down the amount of methane we emit. Like if we emit half the amount of methane this year, we would chop in half the peak of this curve, this methane curve. So this calculation comes from a reduced complexity climate model simulation. So it's not something that can be cited in the literature, but you can also calculate it just using methane's global warming potential with a 10-year time horizon. And so I put a link here, which is where you can find the calculation. If you did want to use this stat and cite something, you can cite that webpage. So the fourth and fifth facts are about methane action benefits. The fourth is the climate benefits, and the fifth is the air quality benefits. These are new stats that just came out of the Global Methane Status Report, which was just launched recently. And so it's basically showing the full implementation of existing methane mitigation technologies. Again, no emerging innovations, no dietary changes, could avoid around 0.2 degrees C of warming by mid-century and could save around 180,000 lives and 19 million tons of crops by 2030 annually. So these are just some good numbers that are very recent and updated. And just a quick note on why methane action benefits air quality. It's because of this ground level ozone that is not only a greenhouse gas, but is also a toxic air pollutant that damages plants and animals, and we're included in animals here. So it leads to respiratory challenges and other health concerns. So those are the 5 factoids. And now just quickly, some of the main resources that are out there that you may already be familiar with, and many of you may have ones that you prefer. I think the chat is open. I don't know, Monica, if the chat is open if you want to throw in other resources that you like that would be helpful for other people. I flagged these ones in particular because these are ones that I know to be credible and vetted. There's a lot of content out there. There's a lot of inconsistencies out there. Please feel free to reach out to me in the future if you're confused by conflicting information that exists, and just know that these are things that I feel strongly represent the science really well. And so the first two are the Climate and Clean Air Coalition methane reports, the Global Methane Status Report that I just mentioned, but their global methane assessment in 2021 is still really good and valuable, goes through individual sectors and all the different technologies that are available to reduce emissions, also talks about dietary changes, looks at costs of individual sectors, puts it all together, looks at air quality benefits. Some of those air quality benefits are updated in the Global Methane Status Report, but it's still really, really good resource. The IPCC reports, those are on one hand, like the gold standard for like the best climate change knowledge that we have out there, but it's everything. It's everything you can imagine about climate change. And so it is hard to tease out the methane things in particular. Specifically in AR6, the sixth assessment report, the physical science basis had a short-lived climate forcer chapter. That's chapter 6. It was really exciting for our community to have the short-lived climate forcers be featured in their own chapter. But what it meant is that a lot of these short-lived climate cooling pollutants were bundled together with the climate warming pollutants like methane, even though they have different sources. And so it was really hard to tease out the individual roles of methane, for example, versus aerosols and all sorts of things. So there's still a lot there that can be very valuable, but it is tricky, and know that even for an expert like me, it is tricky for me to find the information that I'm looking for. So just a note on that. But it really is the gold standard. It is the ultimate consensus. Now that I'm even part of the process, everyone in the chapter has to align on every single decision. And so it's just the whole thing is a very credible resource. So I'll talk a little bit more about the IPCC reports in just a second, but just going through the rest of this list quickly. The Global Carbon Project is really your best resource for current global methane budget. It has not just human sources, but also natural sources, and it has it over different methodologies for estimating things and comparing things. It really is like the best place to go for the latest information on what we're putting into the atmosphere, and what's naturally going in the atmosphere, and then how things are being removed from the atmosphere. The sixth one here, the 2 Degrees Institute Global Methane Levels. I really like this one in terms of being able to look at concentrations of methane going back, I think like 800,000 years from ice cores in Antarctica. And it has really user-friendly tools where you can just get a snapshot of whatever time period you're interested. So if you don't want that full period, but you just want 1,000 years versus you just want the last 20 years, you can grab that screenshot and it can give you the figure that shows the methane growing over time. It also has N2O and it also has CO2 and it also has temperature. For number 7, the EPA, this still exists as of right now. So obviously EPA, it's a little tricky right now with climate change knowledge, but they did in 2025 update their non-CO2 greenhouse gas emissions projections and mitigation. They have tools, they have data. It's really amazing the level of detail they go into in terms of mitigation measures and costs for different non-CO2 greenhouse gases. So I consider you to I suggest you check it out if you aren't familiar with it already. Then the 8 and 9, I have some resources from my organization. One is a livestock enteric methane mitigation roadmap. This is specifically for enteric emissions that we don't know how to reduce right now. For example, we have feed supplements, which are great if you are close to the food that the cattle's eating, but for the many cattle worldwide that are just grazing on pastures that we don't access their food on a daily basis, we don't have good solutions. So this roadmap looks at all the emerging innovations that are out there and provides a roadmap for going forward. And then the 9th one is a warming-induced greenhouse gas emissions overview. So I didn't touch on this in the presentation, but essentially we have a new methane emissions issue emerging with a warmer planet. We have more methane emissions from sources like permafrost and wetlands. And so this is concerning, and this will also affect methane concentrations in the sense that even if we're mitigating as much as we think we are and we say we are, methane concentrations may still be rising just from these natural systems emitting more. So we need to better understand that. And then finally, methane removal. Happy to answer questions about that in the Q&A. But the National Academies has a really great report on an overview of methane removal, what it is, how viable it is, and suggested path forwards for more research and funding and to see if that is a solution that could work in the future. Okay, just very, very quickly, and then we will go into Q&A, just about the IPCC reports. So they are broken down into 4 different reports that make up one assessment report. So there's the physical science basis, then there's the impact and adaptation, which is the second one, which I don't have listed here. And then there's the mitigation of climate change, which is the third one. And then there's a synthesis report that comes out after that brings all this stuff together. And so for methane, usually you would go to the physical science basis for things like how methane is impacting the climate today or in the future based on future scenarios. But then the mitigation of climate change would go into specific sectors, for example. I personally have not found a lot of value in the mitigation of climate change from AR6 in terms of separating out methane. Please let me know if you think otherwise. But I'm hoping that AR7 will do a better job at that. I know some of the authors on that report that are focused on methane. So I'm hoping that AR7 will do a better job. That said, AR7 isn't expected to come out until 2028, I think. So we have time. But just to be on the lookout for when that happens, and hopefully there will be more clarity on the role of methane mitigation in reducing warming over different timescales. The physical science basis, that's the one that I'm a lead author on specifically for future scenarios and global temperature changes. And so I am also aiming to do as best of a job as I can with being very clear about methane's role relative to everything else. So happy to also answer more questions about the IPCC, but it can be a complicated process and set of reports, but it also is the most influential body of work on climate change. So most stakeholders look to it for guidance and information. And at the same time, it can be really dense and hard to pull things out. Okay, I will stop there. Back to you, Monica. Looking forward to Q&A. Thank you.
Thank you, Ilissa. Okay, that was fantastic. I want to turn it right back over to the crowd